Thank you for attending this talk on designing balanced systems for small to large scale deep learning training. I am A.K. Roy, Director of Deep Learning Training Systems and Solutions for Intel's Artificial Intelligence Platforms Group. Today, what we'll do is start with a quick review of deep learning training workloads, complexity and characteristics, and their trends. And then we'll go on to discussing the system design considerations to design balanced, scalable deep learning training systems. And I'll finish this talk with a call out to our OCP work group and partners with whom we are building scalable and balanced deep learning training systems, and a final call to action. Deep learning training models have grown in complexity exponentially over the last few years. In terms of the number of parameters in deep learning training models, the number of parameters have exponentially increased to about 10x per year over the last several years, from about 25 million parameters only a few years back to over 50 billion parameters this year, and will most likely push on to 1 trillion parameters sometime over the next couple of years as customers solve bigger and bigger problems. Supporting the large increase in model parameters is the exponential increase of training data set sizes, as well as, of course, the need for bigger and bigger compute to support the larger models and the larger training data set sizes. Other trends include increase of unlabeled data and semi-supervised and self-supervised learning, as well as training methodologies going on from data parallel, which is predominant today, to model parallelism to comprehend the large model sizes, as well as a mix of data parallel and model parallelism, which some experts call pipeline parallelism. Going a little bit deeper into the training models and characteristics, we can categorize deep learning training workloads and use cases into 3 broad categories. The first one is vision, which are models that process and interpret images or videos for actions or objects. Vision models are already up to 1 billion parameters in size today, and unique characteristics of vision workloads and use cases is the need for high deep learning compute density, significant CPU pre-processing to pre-process the images and videos, as well as the need for large memory capacity for the large images. An Intel study this year has shown that larger memory capacities actually improve the training time to train for these models, especially for medical imaging models that use this 3D unit model. A second deep learning training workload category are language models. These models interpret spoken or written user input and respond appropriately. Language models are unique in the sense that these are the models that have gone to 50 billion parameters today. The large model sizes of these use cases drive dense deep learning compute requirements, as well as high bandwidth communication between the accelerators across which the deep learning models are split across. A third workload category is the recommendation engines, and these use cases are, for example, use cases that run on online stores that recommend products for online store users. Unique characteristics of this kind of workload are a mix of accelerator as well as CPU compute, sparsity processing, as well as a large memory capacity and bandwidth. As we can see that across these 3 different categories of workloads, there are different system requirements, and a balanced, scalable deep learning training system would need to be flexible to comprehend all these kinds of requirements and deliver a system that would be TCO optimized for these workloads. Let's go on to talking and discussing more about the system design considerations to deliver balanced, scalable training systems from small to large scale training. The 5 design domains that need to be comprehended to deliver balanced, scalable systems are: first, the AI acceleration; second, the fabric that connects AI accelerators; the third is the integration and balance between the accelerators, the fabric, and the CPU hosts. The fourth is the infrastructure that supports the accelerators, the fabric, and the CPU hosts in terms of the storage pipeline, the power and cooling. And finally, the fifth design domain that needs to be comprehended is the system software that needs to orchestrate and utilize this deep learning training system. We will go into each of these 5 design domains in the next several minutes. I'm going to use the Exascale GPU that was disclosed by Intel last year in this discussion. The Exascale GPU, otherwise called Ponte is Intel's GPU that balances compute, memory, connectivity, and reliability for AI workloads from small to large-scale AI training workloads. As we talked about in previously, the first design domain that needs to be comprehended to design and deliver a balanced, scalable system is AI acceleration. And this Intel Exascale GPU is particularly suited for the AI acceleration capabilities that need to be delivered as part of the balanced, scalable system. The key requirements in AI acceleration is the dense, efficient deep learning training compute in terms of the data types, in terms of the matrix multiplication types, as well as being able to complete the convolution and the matrix multiplications efficiently in a manner where the data is not being moved around too much on the AI accelerator, while keeping the compute density and compute density per watt at a very high level. And that's what the Exascale GPU Ponte actually delivers. In addition to having high performance, deep AI acceleration capability, because the model sizes have exponentially increased and will continue to exponentially increase, as well as the training data set sizes have increased and will continue to increase, we need an efficient fabric connecting up hundreds to thousands of Exascale GPUs or AI accelerators in an efficient manner. And the link that is built in the Exascale Ponte GPU is a link that has these specific capabilities that allow hundreds to thousands of Ponte GPUs to be connected together in an efficient, scalable manner. The Exalink in these GPUs also deliver the shared memory model capability, where hundreds and thousands of GPUs can be connected together into a single memory model, which can be shared across the GPUs, as well as host CPUs that are connected to the GPUs in the system. Going on to the CPU host integration, to deliver balanced and scalable, flexible performance from small workloads to large workloads, you need a balanced integration of the Xeon CPU hosts with the AI accelerators, so that the right mix of computation can be done on the AI accelerators with computation in the CPU hosts. And the Exascale GPU Ponte Vecchio with the Xe-Link, connecting the GPUs together and connecting the CPU host together in a single scalable system provides the scalable integration that is required to deliver balanced, efficient systems that can not only complete training of small training models, but also can complete efficiently large training models with billions of parameters. Using the Exascale Ponte Vecchio GPU with its Xe-Link connected up with an Intel Xeon processor with a CXL or Xe-Link type fabric capabilities, we can build scalable systems to thousands of accelerators in what we would call a super pod with the right optimum mix between accelerators and GPUs. For customers that have workloads that tend to favor a higher mix of CPUs to GPUs, we can design a flexible system with maybe a mix of accelerators to Xeon processors of 1:1 mix. For customers that run workloads that need less Xeon compute and more GPU compute, we can scale the system with a mix of 1:4 between Xeon to Ponte Vecchio GPUs. So with the Ponte Vecchio GPU, with its dense AI compute and its Xe-Link fabric, and with the CPU, Xeon CPU with a CXL-based fabric, we can design a balanced, scalable system that can scale to thousands of Ponte Vecchio GPUs. Going on to the infrastructure, once we have the accelerators, the Xe-Link fabric, and the Xeon hosts, the next innovation and design domain that we need to deliver is the infrastructure, which is the storage pipeline, the Ethernet or InfiniBand connectivity of the storage pipeline to the GPUs and the CPUs, and of course the power and cooling. And here, Intel has specific capabilities, including the 3D X-Point Optane memory technology that allows us to deliver highly efficient, high-performance storage pipeline to feed the GPUs and the CPUs, as well as technologies such as the Barefoot Tofino technology that allows the Ethernet networking to be optimized to the highest performance level to support the storage pipeline to the GPUs and the CPUs. Finally, we come to the system software. Once you have a large training system with hundreds and thousands of GPUs and CPUs connected together with the Xe-Link fabric in a shared memory model, to efficiently utilize such a system, you need system software that can orchestrate in a flexible manner. For example, if you have many small scale training workloads, the system software needs to be able to efficiently orchestrate and provision the large training system to be able to run several of these small scale training models in an efficient manner. Now, if you have a large model with a trillion parameters, then again, the system software needs to be able to orchestrate that one large training job onto the overall system in an efficient manner. In addition to orchestration and flexible orchestration, the system software needs to support telemetry and reliability so that a training job that can take days to complete on such a system, in case there is some reliability problems, can be restarted in a flexible, efficient manner. So system software is very important to be able to deliver a TCO-optimized, balanced, scalable training system. Now, let us talk about the OCP, OAI, and OAM work group partners that we are partnering with to deliver such balanced, scalable training systems. I'll call out Inspur, Hive, and ZT, the three partners that we're working with to design and deliver balanced, scalable training systems to our customers and the market. Please take a moment to have a look at their presentations and their system designs. Finally, a call to action. Please partner with us, Intel, and our OCP partners to unlock accelerator performance to deliver optimally balanced systems, balanced across compute, acceleration, and communication for deep learning training workloads, and engage with OCP server and OAI work group partners and participants for developing interconnect technologies, multi-chassis scaling, and power and cooling issues. Please visit the OCP OAI work group links, as well as register for mailing list. Thank you for attending this talk. The key takeaways, again, from this talk should be the 5 design domains to deliver balanced, scalable training systems. The 5 design domains are AI acceleration, fabric, CPU host integration, infrastructure, and system software. Thank you.